Hello everyone, and thank you very much for Robert Marty inviting me to attend this conference. I'm Zhipeng, and my topic is Hemisphere differences in response of sea surface temperature and sea ice to precession and obliquity. I will show from these four aspects: scientific issue, model and experiment design, and the results and discussion, the different response of the sea ice and sea surface temperature to precession and obliquity between the two hemispheres, and our conclusions. As we know, astronomical forcing is one of the most important drivers for the climate changes, especially during the last 14 years. The astronomical forcing for the paleoclimate is widely accepted and widely used in the research of the paleoclimate. But the regional response of the climate system to precession and obliquity is still need more studies. In addition, both proxy and modeling studies show that the climate response to astronomical forcing depends strongly on regions and on different climatic variables, but the related processes and feedbacks are still unclear. So, in our study, we selected two of the most important climate variables, sea ice and sea surface temperature, to discuss the different response to precession and obliquity between the two hemispheres by the numerical simulation. The model used in our study is Louvain, which is a three-dimensional Earth system model of intermediate complexity, and the atmosphere, ocean, sea ice, and vegetation are four coupled. Due to the intermediate complexity, it is very suitable to do the long transit simulation in order to only discuss the response to precession and obliquity, and exclude the influence of greenhouse gases and ice sheets. In our experiment, only insulation varied with time. The greenhouse gases and ice sheet are kept constant. Our experiment started from 5011 kABP to 417 kABP, which including the -13 and -12. It is more than 19,000 years and without acceleration. Now let's see our results. First, we will see our sea ice results. This red line represents the precession. The black line represents the obliquity. The pink line represents the simulated Arctic sea ice, and the green line represents our simulated South Ocean sea ice. From this picture, we can see the Arctic sea ice is dominated by precession. The South Ocean sea ice is more dominated by obliquity. In order to discuss the different response of the Arctic and South Ocean sea ice to precession and obliquity, we also analyze the seasonal variations of the Arctic and the South Ocean sea ice. This picture shows the seasonal variations of the Arctic sea ice. As we can see, the annual mean Arctic sea ice variation is dominated by its summer variation. The summer Arctic sea ice variation is countered by the summer insolation, which is dominated by precession. So, the annual mean Arctic sea ice variation is dominated by precession. Compared to the seasonal Arctic sea ice variation, the seasonal South Ocean sea ice variations show more weighted variations, although the summer South Ocean sea ice is still show the largest variation. In addition, the summer South Ocean sea ice is dominated by obliquity. So, the annual mean South Ocean sea ice is dominated by obliquity. Obliquity can influence the South Ocean sea ice through two ways. First, obliquity can directly influence the insolation. When obliquity is low, the high latitude receives less insolation and more sea ice formation. On the other hand, when the obliquity is low, the high latitude receives less insolation, but the low latitude receives more insolation. So, the insolation gradient becomes large, and when the westerly becomes strong, so more sea ice formation. So what are the internet processes? As we know, the sea ice is directly influenced by the sea surface temperature, which is controlled by the surface energy budget. Also, the sea ice can influence the sea surface temperature, we will discuss later. When the, sea, when the surface energy budget is low, the sea surface temperature is low, and tends more sea ice formation. As we can see from these two pictures, the North Hemisphere sea surface energy budget is dominated by precession, but the South Hemisphere surface energy budget is dominated by obliquity, which can explain the different response of the Arctic and South Ocean sea ice to precession and obliquity. The different response of the annual mean sea ice between the Arctic and the South Ocean to obliquity and precession is related to the different geographical location. The Arctic is located in the north highest paleo latitudes, where the variation in summer insolation is very large, and the South Ocean is larger. It is more sensitive to the total insolation, which is only a function of obliquity. Okay, now let's see our simulated sea surface temperature results. The left figure represents the North Hemisphere results, and the right figure represents the South Hemisphere results. As we can see, the sea surface temperature in the North Hemisphere and the South Hemisphere low latitudes are both dominated by obliquity, by precession. Precession and obliquity have almost equal significance in the North Hemisphere mid and high latitudes. In the South Hemisphere mid and high latitudes, the sea surface temperature are dominated by obliquity. Same as the sea ice, we also analyze the surface energy budget. For instance, the North Hemisphere and South Hemisphere high latitude. As we can see from this picture, the North Hemisphere high latitude surface energy is influenced by both precession and obliquity. But the South Hemisphere high latitude surface energy budget is dominated by obliquity, which will agree with the sea surface temperature results. This difference is due to the large area of the South Hemisphere oceans, make it more sensitive to the total energy over time, which is only a function of obliquity. The vegetation and sea ice feedbacks can amplify the precessional signals in the North Hemisphere sea surface temperature. Okay, last. Let's see our sea surface temperature near the equator. As we can see, from 511 to 417 KABP is totally about 14,000 years. It shows 4 peaks. So each cycle is about 10,000 years. The very clear half-precessional signals. For the later part, the half-precessional signals is not obvious. This is due to the large amplitude variation of obliquity. In order to discuss the forcing mechanism of the half-precessional signals, refer to the half-precessional signals and compare it with the maximum insolation at the equator, which show a good correlation. We propose that the half-precessional signals in the sea surface temperature near the equator is responsive to the maximum insolation at the equator. That's our conclusions. The Arctic sea ice is dominated by precession, while the South Ocean sea ice is dominated by obliquity, which is mainly due to the different geographic location. The sea surface temperature in the North Hemisphere and South Hemisphere low latitudes are dominated by precession. Precession and obliquity have almost equal significance in the North Hemisphere mid and high latitudes. In the South Hemisphere mid and high latitudes, The sea surface temperatures are dominated by obliquity. Besides the precessional signal, the sea surface temperature near the equator also contains strong half-precessional signal. It responded to the maximum insolation at the equator. Our results published in the Global and Planetary Change. And thank you very much for your attention.